Hi, welcome back to the breadboard. If you remember these, in the past video we looked at how to drive them. I explained that they're fundamentally the same as just a regular LED, just there's lots in the package and then they're commoned up in various ways to allow you to drive them with a minimal amount of wires. Problem is, for instance here you've got 8 times 8, so you've got 64, you've got 128 segments here. Then if you were having them all on at once, that's 128 times 20 milliamps. That's quite a bit of current. And even when you multiplex them, you've only got one segment on at a time, which means that you've only got 8, because these run independently. So you'd have 8 LEDs on maximum, and at 20 milliamps each, that's 160 milliamps for one segment. Now, if you're driving like in the matrix and you want full brilliance, you have to increase the current. So you could be pumping in, well, per LED 20 milliamps, and it's only on 1/8 of the time, so you could be pumping in over 100 milliamps on an individual LED. Now in the example I showed you, I didn't measure the current, but these were quite bright, and the chips that are driving these are quite capable of doing that. But if you are running a battery operation and perhaps you wanted to run this from a 4-volt lithium battery, or even a 3-volt little button cell, then this really wouldn't work, because you would flatten that battery really quickly. So what do you do when you're faced with a situation like that? How can you reduce the power? So let's have a look at a data sheet just so we can see what currents are involved to drive these displays. 7-segment, 4-digit, or 8-segment, I guess if you include the decimal point. This one is a light on. The only difference between this and what I have on the display is that this has a colon, so it could be used with clocks as well. So you see here we've got the 2 dots for a colon, but that's just another couple of LEDs. Here's your typical wiring diagram. So we've got the common anode. So here we are for absolute maximum ratings, which you normally wouldn't want to run these at because they wouldn't last very long. So power dissipation per segment, 75 milliwatts. Peak forward current per segment is only 100 milliwatts, and that's for a 10th duty cycle. Here we've got the normal operating parameters. So you can see here that we have, for an average luminous intensity, we're driving it with about 10 milliamps. Before I was saying about 20, but older LEDs you would drive them higher. More modern LEDs you can drive them with lower current to get the same intensity. But they're also showing here 20 milliamps for peak emissions. Now obviously this is getting close to the maximum milliamps that you're able to drive it, which was 25, but let's just take 20 as the maximum. So let's just go with an average intensity of 10 milliamps for our calculations. As we saw here, absolute maximum current is 100 milliamps. Now if we've got 8 segments and we're scanning through them, then they're only going to be on 1/8 of the time rather than a 10% duty cycle, which means you can't have this much current. So if we back that off, if we were base it on the fact that we are using 10 milliamps for maximum and we want to get a similar intensity, then we'll probably want to put about 80 milliamps through the segment when we pulse it. And that's what these chips will be doing for us. So 80 milliamps times, so let me just calculate that while we're talking. So 0.08, and there's 8 digits if we had them all on, so times 8 is 640 milliamps on one segment. And if that is an average voltage of, where's the volts, forward voltage, it's probably about 2.5 volts, not there, that's reverse volts, yeah, 2.6 volts max, 2.1 volts typical. So let's just say 2.3 volts. So 0.64 times 2.6, no, times 2. We'll just say 2.4 volts. So that's 1.5 watts dissipation. That's going to eat up a battery pretty quick if you're running it that high. Now obviously you can reduce the power consumption quite considerably by reducing the current and therefore the brightness of the display. But no matter what you do, if you're using a button cell or something like that in a low power application, it's not going to last very long. I had come across a company that specializes or at least is producing a ultra low power display. Now remember, I just said that this is dissipating about 1.5 watts if you're running it at maximum, but even if you're not, let's just say 1 watt of dissipation. Obviously you're scanning that across a number of digits, but that's nevertheless, you're still going to be doing the same thing, because that current, depending on what you're showing, is going to be still getting drawn to illuminate those displays. So if we just say 1 watt, maybe in this display where you have, say, 4 digits or even just a single digit, you're going to be dissipating about that's 1 watt of dissipation, but that's still across the 8 digits as you're scanning through. So this will be a 1 watt, but only 1/8 of that, so 1/8 of a watt while it's on, because it's on for a very short time, but they're all going to be scanning through. So you're still going to have that 1 watt or 1.5 watts of dissipation. How do you get that massively reduced? Well, you can go to LCD displays or something like that, but they're still a bit more expensive and you need a backlight. But the company that I reached out to, they sent me one of their kits, and this company is called Ynvisible. It's from Europe, and this is the kit they sent me. Let me just move this out of the way, and let's have a look inside what they sent. First bit, QR code to their site, getting started with their displays, and here are some of their displays. So now the reason some of these are not in this case is because I have them already hooked up, because I prepared some examples to show you. But what we have here is a 2-digit 7-segment display, various icon types of displays, a couple of 3-digit kind of bar codes, bar graphs, and an 8-digit bar graph, and then we have a single-digit 7-segment display as well. And the two that are not in here are both also 7-segment displays. There's no decimal point on these particular ones, but there's no technical reason why you can't have one added if you want to. Now, as a kit, the kit is not very cheap. I think it's 180 euros or something. But what you get with the kit is you get all of these displays, these samples here, and you also get, let me just back out display. So you get the sample sheet, you get a clicker driver, and you also get a breakout board. Here's one that I've got with a 7-segment display hooked on it. Let me just zoom in again. So it's got a 7-segment display hooked into it. And then they have what they call a driver board with, and I've just hooked up another 7-segment display right now. And this one actually has an ATmega 328p on it, running some software to drive this with some support circuitry. So let's go look at the data sheet and see what this requires to drive it. So this is the kit, 7-segment display kit. This is the one I've just shown you. So like I said, you've got your 7-segment display, driver kit. Here is one of the displays hooked up to what they call the clicker. All it does is apply a signal to the display to illuminate it. Here's one on the driver board showing specific segments being lit up. So let's just get back away from that again. Here are some display parameters. So reflectiveness 40%, contrast ratio 1.3, thickness is only 200 to 300 micrometers, so very, very thin. If somebody wants that in metric, well, it's very thin. It's certainly, like just a few thou. Response time is 100 to 1000 milliseconds, so 0.1 to 1 second. That seems quite slow, and it certainly is compared to an LED. But for a human eye, you're not going to see anything quicker than that anyway. The drive voltage for these are plus and minus 3 volts, and we'll get into that as we go through. But look at the energy consumption here. 1 microjoule per square centimeter of display surface. 0.25 microjoules pulse energy. So when you turn them on, they will take a pulse of energy and then it would settle down. They have the ability to stay on even if the power is disconnected, certainly for a certain period of time. Or the image that you've illuminated by putting a charge on them stays there. I'm giving away a clue how these operate just there. Work from -20 to +80 degrees C, and they will last for an activation cycle of over 100,000 cycles, and often, a lot more than that. So you wouldn't use these for something like a digital multimeter or something with rapidly changing displays, because it would wear out very, very quickly. But if you were using it to show, say, temperature or a status indication or something like that, then it would be more than adequate to last years and years of useful service. Here's the different adapters that you can get. The biggest thing that I'm going to be focusing on is going to be this one, which is just effectively just a breakout board. I will show you each of these as we go through anyway. Here's some linked information, typical uses. You can see here that they're showing them being built into credit card type applications and stuff like that, which is really, really cool. They're flexible, of course. They're printed onto plastic, which is really cool. And so you can pretty much order whatever kind of shape segments you want, custom graphics, etc., etc. There are some limitations, but you just talk to the company and they will work you through it. And there's also more information here. These are actually electrochromic displays. So it's a multi-layer device. As I said, it's actually just printed like a normal printing press. Here's a picture of kind of manufacturing right there. So they're just being printed in a similar way as you'd print a newspaper or something. Obviously multi-layers, because you got to put your electrodes in and things like that, and the wiring. So you can read all this yourself anyway, so I'm not going to go into more of what's on there anyway. A little bit of video on using the adapters. I'm going to go through that anyway, so I'm not going to waste your time showing you the video. 3 adapters, where to start. You've got the clicker, the driver board, driver hardware. When you're using the driver board, you can use anything that basically outputs an I2C signal. 5 volt compliant, but it will work with 3.3 volt devices as well. They're using it with an Arduino script. I have that all set up to show you. And that's the whole point of this. This is still kind of a tutorial, but I'm showing you a special device here. And I'm also going to show you how to simplify the code for driving displays. There is a driver library downloadable, and as well as a data sheet, so that it helps you get going. Now I'm going to show you how to drive these directly as well. I will show you using the library too, which actually talks to the adapter. This one, it talks to this ATmega 328. Let's look at the data sheet, because I had to figure out how to drive these directly myself. You call it semi-bistable because it will remember what you had on the display for 15 minutes or more. I'll show you that as we go through too. Talked about that. Electrochromism, a phenomenon of a material changing color when a voltage is applied. You can almost think of this as a capacitor, only you're using a differential voltage on the display to change its color. And I guess because it will slowly degrade over 15 minutes or something if you don't refresh it, then it's kind of a bit like a capacitor too. You can put a charge on it and then you can disconnect the voltage and it would still retain that charge for a certain amount of time. Internal resistance and things like that would slowly degrade the charge in there, and therefore the display would return to a neutral kind of color, I guess, in this case. They call it coloring and bleaching. So coloring is where you switch it from a bright to a dark state. Dark state is where you see what you want, although I guess you technically could reverse that. And then bleaching is where you take it from a dark to a bright state again. In all of the samples I have here, the background of the displays are kind of a neutral gray color, so both states are visible. But I guess technically you could get the background the same color as the bleached or closer to it, so that the colored, i.e. the dark state, is more visible. Reflective display, yeah, modifications. Okay, so characteristics up to about a 40%. Let's have a look. Where's the viewing angle? Up to about 90-degree viewing angle. So probably 45 either side of straight on. Bistable time. So the contrast from 100% minutes without power. So you can see it's going up to a couple of hours here, where it's dropped down to 75-ish, maybe 50% of the contrast. So it looks like it could last quite a while. But I think that depends on how much you charge it as well, like when you initiate it. Okay, thickness, that's in micrometers. Weight, very little. Bend radius, 10 millimeters. So you can see you can bend these quite tightly. Timing characteristics. So when you apply 3 volts to the display, and we're talking about a 4 square millimeter section here, it takes around 200 milliseconds to take that display to its full colored condition. When you're bleaching, i.e. returning it to its bright state, it looks like it's indicating that it's going to take about 160 milliseconds. Okay, let's have a closer look at the kit. I've got a few things already taken apart here and connected to things. So what I've got on the top here, this is the sheet that you get with the kit. It's usually got these other pieces already embedded in here. These are all printed together, and they're just a sample set. So what you've got is 1, 2, 3 7-segment displays, a 2-digit 7-segment with a polarity indicator. You've got a bar graph, and you've got some icons as well, like an X, a little warning, an on, an OK, big square, tick mark, and we've got a couple of larger bar graph kind of displays here as well. What also, put those aside for the moment, what also comes with the kit is a clicker. That's what this one is. What you can do is most of these displays, except for this one, can just plug in here. When you press the on or the off, it merely will either brighten the entire display of the active area, or it will darken it. And what you're seeing here as this cycles through is, on both of these, is this is the darkening side. The one on the right is being driven directly from an Arduino Uno. It's actually running at 5 volts with a crude hack for giving a differential signal for the ground. Sorry, not for the ground, for the common. Got to be specific about that because I'll explain in a little bit. The one on the left here is driven by another ATmega 328, but this one is configured with an op amp, probably in using PWM, so that it can set the correct bias voltage, so that it can flip the value correctly between plus 3 volts and minus 3 volts to give a slightly better contrasting and switching display. I just wanted to play with how easy it was to switch directly as well without having to have any complicated circuitry. So the clicker, just go through these one at a time. So the clicker here, you can just plug in any of the smaller displays, as I said, any of them except for this one. So let's just take this X, for example. It's off right now, or it's in its bright mode. You would just plug it into the end, click it down, and then when you press the on button, there it is in its dark mode, and off in its bright mode. So these will last quite a while when they're on in this mode. They will slowly fade away. But what we'll do is I'll just unplug this right now. Right, you see it stays on. We'll leave that around for a while, see what it does. Here's a bar graph. What time is it right now? It is 10 to 7. So let's plug the bar graph in. We can see we can do the same thing with it. It's just connecting all of the segments right away. So we'll turn all of those on. We'll see how long these last without any power connected. Now to use this bigger one, I have to plug it into here, but for now I've got a piece of code running which is on from another Arduino Uno. This one is from Elegoo. So it's just a regular Arduino Uno, and I'm using the I2C interface on analog 4 and 5 to talk to this board, which comes as part of the kit, and it's then in turn driving the display here. So I've modified the code that was supplied by Ynvisible to be able to drive all of these displays, because as it came, it was set for driving just one of the displays, which I think was the bigger 2.5 digit one, this one here. Now I've modified it so that I can drive pretty much any of these more complex displays. So let's go look at the code. Okay, so just going to the website a second. When you're using the driver, you need to obviously set up the required library for the Arduino Uno and send the required commands from it under software control. Just connects via an I2C interface quite easily. 4 jumpers is all you need. If you don't have an Arduino IDE already, you can just download it following the link, or just go straight to arduino.cc to download that. The library is also linked to here. Connecting it tells us how to connect it up, pretty straightforward. Here's an example, which is the same as what I have on my display right now in use. And here is the code that they provide. And you can see here that here's the I2C address of the secondary ATmega328. It's telling it it's got 15 segments, which is the number of segments that are available on the bigger display. Driving this display is what this initial code is set up for. So you can see it sets the I2C address. That's just setting it up as an int variable. This is the coding portion, if you haven't guessed. It sets the number of segments that we're driving, which is 15 in this case. That would be for the bigger display. So this one has 15 segments, 7 for each digit, and then the minus symbol in front of it. These other ones only have 7 segments, not 15. So go back to the code. It includes the library, as you can see here, r._ecd_i2c, etc. And invokes an instance of the library as a class name with ECD, passes in the I2C address and the number of segments that are being used. And then there's nothing in the setup, and then it just has a loop where it counts from -99 to 100 and outputs the display, waits 5 seconds, and then just keeps counting up until it gets to +100, and it just keeps looping that. So what is in the library? Let's have a quick look here. I've got it open here. Display it updated to the new state by passing in arrays of 1s and 0s in a Boolean array. Refresh the display, set the switching time, changes the switching time in milliseconds. The default value is 2.2 seconds. That's why you can't go too fast when you're using this unless you update this time. It will affect the contrast if you drive it quicker. So longer switching time generally means better contrast. So you can see here the set counter voltage changes the counter voltage to voltage, whatever the value you put in as a float. Should be between 0 and 5 volts. Default is 2.4. And if you vary this, if you bring it lower than 2.4 and more towards 2, you will increase the dark state and less contrast in the bright state, while a higher voltage means more contrast in the bright and less in the dark. Reset, custom functions for specific design. So these are the ones that drive the single digit, double digit, bar graph displays. So that's all of the technical information here about what this is doing. So let's have a quick look at demonstrating. So you can see here right now it's driving a single digit. So let's look at my code. Just so that I can show you what I did with it. It's an extension of that we were just looking at. The difference being, though, that I've enhanced it to handle the other display types. So let's switch to my code. Here we go. So the beginning is exactly the same. Right now I've got number of segments equals 1. The address is the same. I've got a few defines here now, so I can very easily, by just changing the define, I can change the display type that I'm using. So where there is a define, it leaves like a true-false kind of condition. So in this case, I'm declaring a display as 7x1. In the initialization, I've taken the number of segments and I've made it an int. But in the initialization here, what I have is I've used the serial interface just to give me some debug information. But I've got if defined display 7x2, then send out the serial port that I've got that, and then set the number of segments to 15. If it's a 7x1, set the segments to 7. If it's a bar display, the segments is also 7. Now, these three functions actually don't use the number of segments, but I just included it here. If you were using the binary functions, setting a Boolean array, then it would use it. In the loop, what I've got is very, very simple. It just says if define 7 by 2, call that function. If defined 7 by 1, call a different function. If defined bar display, call a different function. Now, this is through definitions that I've got these in here. I could wrap these if defines around the code as well to keep it very, very small if I wanted to, but I just wanted to keep this simple. So here's my functions. This is one for driving the display directly. I haven't got that coded in there yet. So Boolean is new state, and then you've got some ones and zeros. Right, that's all that does, and then it sets it using the function call. We've got drive a bar display. So we set a number between 0 and 8, and just sending it out to the display, waiting 3 seconds. We have a 7 by 1, where we're simply counting from 0 to 10, or less than 10, so 0 to 9. And we're doing set number, and we're waiting 3 seconds as well. And then for the 7 by 2, we're doing minus 99 to 100 and doing the same thing. So they're all very, very similar. They're just slight differences between them. And obviously a different function out of the library that they're calling. So when I compile and send this to the Arduino Uno as it is, we get the display working the way this one is right now. Okay, so you can see it just counting up with a 3-second delay between each one. Now if I go back to the code and I change the define to the 2 by 7, okay, and I can upload that to the Arduino. Okay, I've just switched to the view so you can see the display while it's doing it. Zoomed in, yep, so counting there. So initially when I upload this, it shouldn't make any difference because it's probably just dealing with a single digit of a 2-digit display. So we're just going to compile it now. Take a moment to compile and upload. Compilation complete. Updating. Anyway, as you can see, it's not doing anything at the moment. If we waited long enough, it probably will update that digit. Yeah, change it to an 8. So it's going from minus 99 to plus 100. So it's now just gone down 10, and now it's just changed that to an 8. So let's just put the right display in. So here is the proper display. Now if I power this back up again with that same code, starting at 98 minus 97, so it's now counting and it's using the double digits, which is great. Now what happens if I want to use bar graph instead? Then go back to the code. I can comment out that one and uncomment the bar display. I'll just pre-compile that for the moment. I'm going to plug the bar display in first. Okay, that compiled. I'm just going to change this display, leaving it on. So we've got the double digit one, the single digit one, here's the bar one. So this is going to be running the bar one with the same display code. So again, it's working on the upper digit, so it's going to take a little while. Now I'm just going to compile this code and upload it. Shouldn't take it long. Compilation complete. Uploading. And there we go, first digit. And it's going to slowly work its way up the bar and then stop. So that's all the demo software using the demo adapter. Driving from an Arduino Uno. Now, if you were using this in a production environment, maybe you had a few of these, or maybe more digits of a display, you would probably use something like an ATmega 328 or one of the other many displays available. Even a 3.3 volt one might even be better because that's the native 3 volt drive for the display.